Hi, my name is Mihir Shah, and I'm joined today by my teammates Alo and Anthony, and I'm supported by my teammates Jim, Yash, and Nick. Together, we're Team Cloud, and we're excited to present to you our solution for injury prevention for electric skateboard riders. In today's interconnected world, the issue of last mile transportation is becoming more relevant than ever before, and electric skateboards are garnering increasing attention. We see more and more members join the e-skateboarding community, and as this is a new technology, proper safety equipment has yet to be invented. Most safety gear is created for normal skateboarders and longboarders, whose falls are very frequent and different in nature due to the dangerous tricks of speedy downhill riding. This new skateboarding community, however, only travels up to 20-25 miles per hour and uses these skateboards as a means of daily transportation. We have compiled a montage of fall videos for you to understand the nature of falls we're trying to deal with here. So, what did all these falls have in common? It was that invariably the rider's arms came up in time to brace the fall. Due to the low riding speeds and the nature of the stance, riders tend to get their feet to the ground first and only then get whipped to the floor, giving them enough time to raise their hands up in protection. A video analysis of over 100 electric skateboarding falls led to the generation of the following heat map, which shows that most riders first land on their hands and wrists. It is also important to note that all these falls resulted in impact with the ground within 1 to 2 seconds after initiation of the fall. Digging deeper to verify this intuition we developed from these videos, we looked into medical statistic reports. We found injury statistic reports that of the 65,000 skateboarding related ED visits last year, a 44% occurred as a result of injuries to the upper extremities, the hands, wrists, and forearms. We conducted our own surveys to verify this through outreach in the skateboarding community, and from a total of 200 responses, 173 of the reported falls involved the user's hands and arms. This percentage is obviously significantly higher than that in the report, since the report only accounted for serious injuries that required hospitalization. Understandably, the percentage injuries affecting arms are disproportionately higher for injuries that do not require hospitalization. Thus, our target audience is the e-skateboarding community that rides as a means of transportation that is excessively hurting their hands and wrists. The several solutions that do exist, stakeholders find to be bulky and outdated. Wrist guards, hand guards, armored hoodies, and elbow guards all fail to be discreet. As for protection, each existing solution caters to only one or two types of protective users. For example, armored hoodies can only protect against skin abrasion, not impact forces. Elbow guards only protect the elbows, and wrist guards only protect against minor wrist sprains. This brings us to our interpreted stakeholder demands and how we came up with our target system characteristics from these. The primary unaddressed demand is that of convenience. Riders indicated they did not want another device to add to what they were already carrying around upon reaching their destination. This guides our design that our device must have a wearable form factor that need not always be removed once you've reached the destination. The second component of convenience was discreetness. What this specifically means is that when worn, it must not be an obvious goofy looking protection device. That detracts from the whole coolness factor of skateboarders. Through surveys and trials with weighted and sized bands, we came up with a maximum weight of 0.555 kgs, which was about twice that of the remote, and a maximum size of 14 centimeters by 3 centimeters thick. Our second major stakeholder demand was of course that of effective protection. More specifically, our users desire protection against wrist and hand abrasion, fractures and dislocations, and sprains. This guides our next two system characteristics, force reduction and deployment time. The main objective for Cloud is to produce comparable force reduction to existing impact injury prevention devices. Helight's hip airbag for the old age and Hovding's inflatable helmet for cyclists both claim force reductions in the 60 to 80% range. Thus, based on this and other CE certification requirements for the arm, our target percentage force reduction is 70%. Our solution must deploy a protective element within less than 1 second of fall initiation, since e-skateboarding falls occur in 1 to 2 seconds. I now hand over to Alo to introduce the final form of Cloude.
After consideration of several solutions, we decided to create Cloude, which is a wearable, deployable wristband airbag. As shown, Cloude detaches at the wrist for easy removal and adjustment and allows for complete dexterity of the wrist so that the user can hold the wireless skateboard remote. Included in Cloude is an airbag, CO2 canister, trigger mechanism, Bluetooth communicators, and appropriate housing. It should be noted that we are not integrating a sensing system into our design as it is outside the scope of senior design. In order to incorporate appropriate sensing, we would need an electronics and injury analysis team with hundreds of fall profiles using intricate and expensive detection equipment. Instead, we are providing space for sensors, an Arduino, and Bluetooth communication that can easily be integrated with the sensing system later down the road. That being said, our three main subsystems are the airbag itself, the trigger mechanism, and the housing and electronics package. We went through several steps before arriving at the final form of Cloude. First, we chose an airbag material and volume as well as the final shape and folding technique it should employ. Next, we created a linear impact device to test and create an airbag model that relates deflation rates, internal bag pressure and stiffness, and gas properties to peak force reduction. Next, we down-selected to a CO2 canister combination as well as tested the requirements to puncture the canister. Our next step was to create a trigger mechanism that releases and inflates the airbag. Finally, we created room for electronics and a housing unit. Cloude addresses all stakeholder needs by being discrete, detachable, and protecting the hands and wrist from fracture, sprain, dislocation, and skin abrasion. The airbag is a subsystem that actually cushions a rider's fall. Since the hand and wrist are the first areas to make contact with the ground, we decided to make a 5-liter A5956 nylon airbag that covers the hands and wrist. The airbag itself is meant for a single use because e-skateboarders reportedly fall at low volumes, around 2 to 4 times per year, and we don't want to compromise the integrity of the airbag material by having the rider use the same airbag for multiple uses. The trigger is the subsystem which punctures the gas canister and consists of a bolt-action style lock, a custom specified extension spring, and a gear-driven housing release system. Cloude comes with a housing and electronics unit. The electronics include 3 Bluetooth sensors, an Arduino Nano, and a battery. This actuates the trigger mechanism upon receiving a go signal. For proof of concept, we manually entered a signal into the Arduino. For further exploration, that signal will be replaced with a fully integrated sensing system. The housing unit holds an airbag, canister, and electronics in place with several covers made from different materials and an adjustable wristband. To generate a successful airbag, we determined 4 key characteristics: the shape, the folding pattern in which the bag is stored, what method would be used to seal the seams of the bag, and the material of which the bag is composed. Since information on material properties is not readily available online, we decided to experiment with different bag materials and shapes. However, we were only able to obtain and test polyester bags. Due to the lack of time in a physical lab during this pandemic, we were not able to order and test more materials. Instead, we gathered what little information we could from Stern & Stern about material selection and included the A5956 nylon bag with a 63 thread count, which is stronger than our previous nylon bag, is the optimal material to use. Overall, we recognize that the geometry of the folded bag must be oriented in a way that allows air being expelled to assist the bag in unfolding. For this reason, a simple roll was eliminated, as the outside of the roll inflates first, hindering deployment. For this reason as well, the Z-fold was found to be superior to all other folding configurations. During our time on campus, however, we were able to test an array of airbag shapes and sizes with variable initial internal pressures and deflation rates. Our final airbag shape is a hollow semi-cylinder whose opening is positioned around the electronics and CO2 canister. We chose this shape because it protects the rider in the areas most affected by a fall. According to our heat map of falls, riders tend to land on their hands and wrist first. Also, people don't land on the inside upward half of their arms. This area, as shown in the CAD rendering, is where we will store the electronics and canister because this area will never touch the ground. After choosing a bag shape, we fabricated a linear impact device, or lid, which consists of a drop plate with a certain mass, an airbag attached to the bottom, and accelerometers. The drop plate was connected to linear bearings which constricted our movement to one motion so that we can definitively say that all the weight from the plate was dropped directly onto the airbag. A valve and tube were connected between the airbag and the airline. Before each test, we used a pressure gauge to fill up each bag to a certain pressure, then recorded the drop test via Excel data streamer. Several criteria were assessed, including deflation rates, initial internal pressure of the airbag, and airbag shape and volume. Our first volume was chosen based on the maximum size that we can fold a bag around the wrist based on stakeholder demands. We then incrementally downsized the bag until we reached 2 liters. Note that the 2-liter bag was the last size we were able to test. We also tested different internal pressures between 1 and 30 psi. After the first round of testing, we found that the peak impact is reduced the most between 1 and 5 psi. Above 5 psi, the bag becomes unreliable and the impact time drastically decreases. Therefore, our further tests were restricted to the domain of 1 to 5 psi. After experimenting with different sealing techniques and creating deflation through controlled outflow holes cut into the airbag, as well as applying a Savitsky-Galev finite impulse response filter to our raw data, we found that a 3.5 psi bag with a deflation area of 2 to 4 square centimeters is the optimal pressure, volume, and deflation combination for our system. This combination provides an 80.1% force reduction, which is comparable to what is being marketed by other airbag products in the industry. This comfortably fits our goal of reaching 70 to 90 peak force reduction. In order to fill the airbag, we need some sort of pressurized gas. There were several options to choose from. Car airbags are inflated as the result of a chemical reaction. Ofting, an airbag helmet for cyclists, uses helium. Helite HipSafe, an airbag for the hip, uses CO2. In our case, we need a gas that is light, cheap, safe to carry around in a wearable device, and can inflate an airbag on the order of 10 liters in less than 1 second. Due to these requirements, we decided to choose a 16-gram CO2 cartridge. By filling our empty cartridges with water and knowing the mass of liquid CO2, we obtained the volume and density of the cartridge. This, paired with Boyle's law, allowed us to determine flow rates and volume fill pressure combinations, of which we can fill our bags. Due to this volume pressure calculation, along with our force test results, we know that our final product will use a 16-gram cartridge to fill a 5-liter bag to 3 psi with a 2 to 4 square centimeter outflow area. One important design decision we made was to puncture the canister on the spot. Most companies, like Helite, pre-puncture canisters. This, however, was not possible for us because we have a restricted design space in which we need all of the airflow from the canister to enter the airbag. This means we need minimal leakage, which is greatly amplified with pre-punctured canisters. To design our puncture mechanism, the first piece of information we needed was how much force it takes to puncture a cartridge. To do this, we designed a testing apparatus which used a weighing scale to measure the torque and thus bolt force to penetrate through the seal. With a safety factor of 1.5, we found that 70 newtons of force would be more than sufficient. Another constraint we considered for our force mechanism was time. The time for fall detection and deployment is 1 second because that is how long it takes a skateboarder to impact the ground after falling off their board. There are 4 major concerns within our time constraint. The first 2 are fall detection through sensors and Bluetooth communication between the sensors and wristbands. According to Helite, it takes 200 milliseconds for their motion analysis and fall detection system, which uses gyroscopes and accelerometers to detect a fall. Communication between sensing and actuation is minuscule as it'll take less than 10 milliseconds. According to the flow rate from our canister, desired internal pressure, and volume of the airbag, it will take less than 400 milliseconds for inflation to occur. Puncturing, which occurs between communication and inflation, thus has a maximum time limit of 395 milliseconds. Now that you know the constraints for puncturing, Anthony will talk about our trigger mechanism.
The final trigger mechanism was designed to optimize space as well as promote user-friendliness and product reliability. The notable design features are the method of force production, the method of locking, and the method of CO2 routing. Force production refers to the means by which Cloude creates the 70 Newton force necessary to puncture our 16-gram CO2 canister. Puncturing via motor torque, gearbox-assisted motor torque, and spring tension were all considered. However, the optimal solution for force transmission was found to be a spring. An extension spring, concentric with the gas canister, was found to be the least volume-intensive configuration. It was verified that this configuration was reasonable via specification of the appropriate spring. We chose a spring with an outer diameter of 27 millimeters and an unstretched length of 16 millimeters. The spring is made of ASTM A228 music wire and is 2.5 millimeters thick. It therefore has a spring constant of 4.87 newtons per millimeter, allowing for the storage of 73 newtons of force at an extension of 15 millimeters. Once the spring was specified, a locking mechanism was required. Locking has two major constraints. First, the release of the locking mechanism has to be within our overall time constraint of Cloude's deployment. After a search directed at this objective, we found that solenoids were the only commonly available devices capable of converting an electrical signal to mechanical motion within our deployment time constraint. After experimenting with various locking configurations, we chose a bolt-action configuration due to its ability to allow us to save space through the use of a rotary solenoid. Various considered locking setups with a linear solenoid proved to be bulky and unconvincing from a strength perspective. The bolt is pulled back, extending the spring, and then rotated to lock in place via the bolt guide. The rotation of the solenoid unlocks the bolt and allows for rapid retraction of the spring, causing the instantaneous puncture that we desire. Second, the lock itself must be able to hold back the force of the spring opposing it. This was verified through force analysis on our bolt. For CO2 routing, the most important considerations are minimizing air loss and the distance of tubing required. This was achieved by routing hollow plastic tubing through the puncture needle and sealing the interface with an O-ring. The trigger subassembly was placed as close as possible to the airbag's push-to-connect fixture. The airbag is held in place by a cloth covering, which is interfaced with hooks protruding from a cylinder on the casing. The rotation of our solenoid in turn rotates a set of gear teeth on the puncture plate, which allows for the hooks to disengage, causing the cloth to fall away and allow for free inflation of the airbag. To enable both airbag systems on each arm to inflate at the same time, we used Bluetooth communication through an HC05 and HC06 module connected to Arduino Nanos, with one arm being the master and the other the slave for proof of concept. Our final product uses an Arduino Nano and a Bluetooth module along with a 12-volt battery to power and communicate with our rotary solenoid for initiation of triggering. The housing is the subsystem which protects the electronics package and trigger, as well as contains the airbag when not in use. The main consideration for the housing is using minimal volume. Topology analysis allowed us to arrive at the shown result. In order to validate our final system, several tests need to be performed. Since we cannot physically perform the tests anymore, we would like to give a brief description of the plans for each system-level validation step. The first test must ensure correct communication between the components of our electronic subsystem and full deployment within our allotted time frame of less than 0.8 seconds. Again, this allows about 200 milliseconds for a future sensing system to detect a fall. First, the puncturing mechanism must be able to reliably receive a signal remotely in order to activate. Second, the auxiliary bracelet must be able to very quickly receive a signal from the master board to deploy alongside the main bracelet within the constraints of our previously allocated time budget. We performed some basic electronics communication validation to encouraging success. The second system-level test is a force validation. Although we've already done extensive force tests on our airbag subsystem, system-level force reduction tests are desired. The apparatus for these tests would be similar to our current linear impact device. However, it will incorporate Cloude fully, with more accelerometers placed around an arm profile and the mass of an average male, around 50 kilograms, on top of the force plate. This will allow us to show that Cloude, with all of its systems integrated, still reduces force in the same way that our airbag subsystem did. Lastly, we must verify that our device is comfortable for our users by conducting user test surveys in which riders try on, adjust, and briefly ride with Cloude on their wrists. While the current circumstances prohibit this, it is certainly a required future step. Here are the subsystems of Cloude again in an exploded view, showing the areas of interfacing into the final assembly. We will deliver this package to the consumer with the airbag packed and connected to the system, as well as provide a CO2 cartridge which will be screwed on. The system will be ready to use upon delivery. After falling and inflation of the airbag, the rider will remove the old airbag and CO2 cartridge, reset the spring using the bolt, and then insert a new airbag valve and gas cartridge. Overall, Cloude meets and exceeds all user needs by being a discrete, detachable device that deploys in less than 1 second and protects the rider's hands and wrists, which are the first areas to contact the ground in a FOOSH scenario. We would like to sincerely thank everyone who has helped us along the way, especially Dr. Graham Wabacheski and our teaching assistant, Jonah Arnheim. We would also like to thank all those who took the time to watch our presentation and look forward to answering any questions that have arisen.